Hi, welcome back on the Subscribe blog. You may have seen the episodes where I discussed Service Bus Premium messaging briefly, 3 minutes, and the previous episode where Dan Rosanova and I kind of brought Subscribe, this blog, back from sleep. And we said we're going to talk more about messaging, we're going to talk more about Service Bus and go into the details. We're starting that today with this talk where I'm going to go and give you a broad overview over Service Bus messaging because we haven't done that in a while. And so I'm going to go back, talk about messaging, talk about why you want it and what we have in Service Bus in terms of capabilities. I'm not going to go down into the API or at the API level or protocol level. We're going to do that in deep dives, but I really want to give you the big picture, ultimately culminating in our new premium product, which is kind of the flagship of the product family. So we'll talk about the platform, talk about some standards, talk about some facts and figures, and talk about the capabilities that we have, just broadly speaking, that we have in the platform. I want to start with some basic patterns, load leveling being one of them. So messaging foundationally is really about getting data reliably from A to B and have some decoupling between this. That decoupling typically results in, with messaging systems, with brokered messaging system, in a push-pull translation. So you push data in and you pull data out. That has some really nice properties and enables some very nice capabilities. For instance, a pattern called load leveling. With load leveling, you can effectively decouple the read side of a system from the write side of the system. What do I mean? If you create a website, if you create a large system, very often there's a ton of people, a ton of consumers that want to read information, that are interested in getting data, more so than writing information. It's very often the case. Whether that's a website or whether that's a service layer, or as we say today, microservices layer, doesn't really matter. Lots of services are set up for providing information to very many people. So you have a website, and the website you can optimize by creating caching on the server, by leveraging the caching capabilities of the user agent of the browser, and also by having caches in the form of caches that are sitting behind or on the side of a web service, or having even content delivery networks. The web is really built for or is optimized for reading information, disseminating information to a huge number of people. In many business systems where you build commerce systems, the write side, writing data, is much more constrained. So a few examples. Think about an airline where you need to fill individual seats. You need to go and check people into particular seats. Well, you only want to have one authority, which is actually assigning those seats. If you are selling tickets for a sporting event or for a concert, you don't want to go and sell tickets doubly. You may want to, or you can go and create writers for particular sections. Let's say you have a concert for a world superstar. Let's say, who are the ladies? Beyonce and Katy Perry, or the Rolling Stones come into town. There's a whole stadium, 75,000 people fit into that stadium, and you want to sell those tickets, and those tickets are going to sell in a minute or two. Well, maybe in 10 minutes. But it's going to go very rapidly. One way you can deal with that problem is you can go and segment this out, partition the problem, but you're still causing a lot of contention on the individual records. And if you allow 100,000 people to show up on your website and you're putting all that load onto the database, doing writes and doing inserts and doing transactions, the database may keel over, and you see that fairly often. So one way to deal with that is to segregate this, to go and put the writes, turn the writes into jobs, and put those jobs into queues, and then have the transactional part go and pull the data off the queues. Now, the website, the user wants to have some feedback, and there's patterns to how to enable this. We're not going to talk about those. They exist. We're going to talk about those in a future episode. But generally, you have a lot of load from the website. You want to have consistent ownership of particular records, that one seat in the stadium or that one seat in the aircraft. And this is owned by a business system, and you want to go and not put the stress of the rush for the tickets On that transactional system, the way you decouple it is put a queue in the middle, and the business process system only pulls as much jobs as it can go and process, so it doesn't get under external stress. That's one way of how you can solve these stress situations and not make the backend crash. The backend may get slow because it doesn't have the capacity, but it doesn't crash. That also allows for batch processing or for offline processing. So if the backend does crash, all the jobs are actually queuing up, but they never get lost. So if you are getting a message into that queue, that job will be seen by the business process backend eventually. The business process backend can go offline, you can go and upgrade it, you can go and bug fix it if you need to, or you can allow jobs to pile up over a period of time for an hour, two, a day, and then only bring a business system up to process them all in one go if you want to. So that's one pattern enabled by queues or by messaging. Two set of patterns, in fact. Another pattern is load balancing. Load balancing requires, obviously, that you have something to balance across. So the first thing you can do is you can observe the queue length, and as you observe the queue length, if the queue length gets over a certain threshold for a sustained period of time, you can spin up another set of resources, more business processes, and those business processes can then pull jobs from that queue in a competing fashion and share the load across them. If the queue size still rises, then you can go and spin up more resources until you get a balance between the input and the output. There's two ways of doing this. One is with a computing consumer model between queues. The other one is using partitioning. Partitioning is something you can do with topics. A topic is like a queue. Fundamentally, you can send the data in, you can pull data out. The topics have the ability to create multiple outs, and those multiple outs are called subscriptions. And for each subscription, you can effectively, every message that gets sent in can be selected in one of those subscriptions. That allows you to do taps. The concept of a tap is that you send the data in, and you can now go and add another, let's say the audit subscription, which sees every message that has been sent to that topic and puts it into an audit log. Another way of using a topic is for multicast fanout. You send one message in and every subscriber gets a copy of it if you want to distribute it across a larger number of subscribers. And the other model is partitioning that I just alluded to. So go back to the stadium scenario. You want to sell the tickets to the stadium within a very short period of time. You could make a rider for each section of the stadium where you want to sell the tickets. So each of those riders owns a section of the stadium. It only writes to those seats. So when people are selecting a ticket and they want to go and then push the button and purchase it, first come, first served, that message then gets routed to the rider, which is responsible for that respective section, and that then goes and makes a call of whether it can go and seat the particular persons, and it can also go and reseat people if it needs to be, or if it can't fill that, it can go and throw the message back into a compensation mechanism. So in the Microsoft Message Platform, we can accommodate all those patterns. We have queues and we have topics, and those topics have subscription rules, and we have this consistently available using a consistent set of APIs and a consistent set of protocols on premises and in the public cloud. On premises or in the private cloud, we have this as Service Bus for Windows Server 1.1. And we have this in form of the Service Bus for Windows Server 1.1 in the Windows Azure pack. Those are software packages you can go and install, and they're included in the licensing of Windows Server and in the licensing options for Windows Azure pack. So that's something you can run on your own hardware, and you operate on your own hardware. Service Bus Standard and Service Bus Premium are things we operate for you in the public cloud. And the nice thing is that it's very easy to switch between them. So you can go and do local development on Service Bus for Windows Server, and you can go and run against the cloud. You can do either way. There are some differences in terms of features between those. And those are mostly caused by the upgrade cycle. We upgrade Service Bus for Windows Server along the upgrade cycles of Server and of Windows Azure Pack or Windows Azure Stack. So we haven't been doing an update in a while, and we're going to do one in a while. But the product exists and is active, and there will be updates. We can do more rapid updates in the cloud because we're going cloud first. All new features that we always build are always going to cloud first. So they go into Service Bus Standard and go into Service Bus Premium, and then eventually they're going to show up in the on-premises product. But the foundational capabilities, sending and receiving messages and all those things, are consistent across the platform. In terms of the numbers for the cloud platform, we have hit some very nice milestones recently. Azure Service Bus Event Hubs, or Azure Event Hubs, has managed to process more than 1 trillion messages per month. Just a few months ago, we're already nearing 1.5 trillion now. Just a few months ago, we had 200 billion message operations on Service Bus Standard. So queues and topics, 200 billion a month, and we're nearing there 250 billion very rapidly. We do well over 6 petabyte of monthly data volume that we pull through Service Bus, and again, that number is very quickly rising. And of course, since we're messaging, since we're moving data around, we're also benefiting from, and you are benefiting from, the massive build out that we have in terms of networking capacity and networking infrastructure across North America and also across the world. We have 85 global internet exchanges where we effectively take over the traffic directly onto Microsoft Fiber, onto the Microsoft network, which means that if you're building globally distributed applications, your Service Bus solutions are going to benefit from running over our dedicated network as soon as we can take that traffic from you. In terms of capabilities, I said they're consistent. We have both Service Bus on premises as well as Service Bus in the cloud, or multi-node clustered message brokers. What that means, I'm going to show you in a few diagrams later in this talk. We're using the AMQP protocol. We have an HTTP REST protocol head through which you can manage resources. You can create queues and topics in event hubs, in the event hub namespaces, and relays in the relay namespaces. And you can also send and receive messages, obviously, through a very simple HTTP API. And the queues and the publish and subscribe topics are consistently available between Service Bus for Windows Server and Azure Service Bus. There's some small differences in terms of capabilities between the two, but most of the capabilities are available across all of them, including that AMQP 1.0 support. One thing that's not available is partitioned entities, not available in Service Bus for Windows Server, and what that means I'm going to explain to you also a little bit later. The storage engine on premises is SQL Server. Reason for SQL Server is that you or the people who are managing your infrastructure know how to run SQL Server. They know how to do the backup, they know how to do disaster recovery, they know how to manage your data, and it's enterprise data, so it's good for them to have existing skills to make sure that if something happens on Service Bus, that they know how to go and deal with that data and restore it in a consistent fashion. So we chose SQL Server also because it's something that people who are managing data know how to manage and also know how to set up in clusters. And SQL gives you a very nice ability to go and create singular stores. So Service Bus for Windows Server runs on SQL Express on a single store, but it also runs on SQL Server fully scaled out, always on, depending on how you like it. Service Bus for in Azure runs, the standard version runs on SQL Azure DB, or on Azure SQL DB to be precise. We also get that replication. And for premium messaging, we've actually made a switch, and we've switched to the Azure Event Hub storage engine we nicknamed Jetstream. And I'm going to talk about that a little bit later. Differences from a management perspective are obvious. Azure Service Bus for Windows Server you manage yourself. And Azure Service Bus and Azure Service Bus Premium Messaging is something that we manage, monitor 24/7, and we also provide full life-side support for. Azure Service Bus Standard is something that where we are giving you pooled resources. Service Bus Premium is something where we give you dedicated resources. So from a resourcing model, a resource reservation model, it's more like IaaS, but I'm going to talk about that also in a second. The AMQP protocol is the core protocol that we support in Service Bus. We still have some remnants of our .NET centric proprietary protocols called SBMP. We're eliminating those over the course of the next few months so that all of the features that we have are going to be fully available in AMQP 1.0. It's a international standard, and the reason why I'm emphasizing 1.0 so much is that there really are multiple versions of AMQP around, and that's worth talking about for a second. This slide says it's broker model independent, and it has no dependencies of broker internals. That was not the case of AMQP 0.9. Most of the AMQP broker vendors have moved over to AMQP 1.0, with a few exceptions that I will not name here, but there are a few. The only standardized version of AMQP is 1.0, and the AMQP working group has abandoned 0.9 because it has broker-dependent features. So there was a particular topology, a particular broker model that was in mind, and it wasn't able to go and accommodate relayed traffic. It wasn't able to accommodate basically arbitrary mechanisms like having event hubs use AMQP, like having queues and topics with particular features have used AMQP. It would have been a more constrained thing. And so the working group then proceeded and built 3 years ago, it was standardized 3 years ago, AMQP 1.0. And that is the only standard version of AMQP, and the version 0.9, which some 1-2 broker vendors are still claiming is the standard, really isn't. That version is an international standard, ISO IEC 19464, and that's the one that we're supporting. And that Apache Cupid and Apache ActiveMQ and SwiftMQ and IBM's MQ Lite are all supporting that same standard protocol. The protocol is also the foundation for the programming model options that we have, where we allow you to effectively come from any platform in terms of client. Service Bus for Windows Server and Azure Service Bus and Premium Messaging have the same protocol gestures. There's a few protocol gestures more that the cloud supports, and that's just owed to the fact that it progresses faster. And we're supporting, as I said, our proprietary protocol, which we're phasing out. Phasing out means that we're not going to cut support for it, but we're not going to emphasize that we're not going to do any more development. So that's why we're talking about AMQP here primarily. And the AMQP protocol is backing our .NET SDK, which many of you are using, which still has support for .cf if you want that. We have a AMQP.NET Lite, which is effectively a light library which exposes more of the primitives of AMQP. That's an open source project that's run by our team, and that is for .NET and supports the universal Windows platform, so Windows 10 and Windows 8 for store apps. It also, and Windows 10 IoT Core, of course. It supports the Core CLR, so the new open source version of the CLR 5.0. It supports Mono, and also supports the small embedded versions of the .NET framework, namely the Compact framework and also the Micro framework. That's for AMQP.NET Lite. And then we have a community contribution, which we're actually very happy about, from Paolo Patierno from Italy. And he took the Service Bus SDK, made a substrate of the necessary APIs to do messaging of the Service Bus SDK. He basically took our interfaces and implemented them into SB Lite, which rides on top of the AMQP.NET Lite. So if you're like the familiar programming model, you can use SB Lite, the SB Lite library, and use that. For everything else, Win32 apps, for Linux apps, for Mac OS 10, for embedded applications, we're contributing code into Apache Cupid, Proton C, Proton J, and that is a library that's from the Apache Cupid project and has become kind of the universal AMQP 1.0 client library. So that allows you to go and write applications in C, C++. or in Java, or there's a whole host, which I haven't even listed, of languages from Go to Perl and PHP, etc., that let you target the AMQP library. If you don't want to use the AMQP library, if you don't want to take a dependency on this, there is bindings for HTTP. We have an HTTP protocol. So we have our Azure SDKs for Python and PHP and Node, etc. Most of them include a simple HTTP client to Service Bus, which is always great for sending messages, and is using a long polling model for receiving messages over HTTP. It's not so efficient as AMQP is, but still fairly efficient. Service Bus queues, going into the detail of the product, they are based on an ordered message log. You send messages in, and the messages get timestamped in order of arrival. Once the messages are accepted, they are held safely in redundant storage. I showed you that. So they're going to SQL or going into our new log. The data is always redundantly replicated. If any of the stores fail, that's not going to be a problem. And we support multiplexing. We support strongly ordered delivery in Service Bus queues. There's really two fundamental modes of receiving messages from Service Bus queues. One is pull. So you use an API to receive messages from the queues. The other one is pushing and forward to into other entities inside of the same Service Bus namespace that you can use for composition, which is very powerful, and I have a dedicated slide for that in a moment. Service Bus topics, as I said, a queue is one in, one out. Service Bus topics, one in, multiple outs. Each subscription that is durably created and named can have a copy of the message. There are all the filters through which you can decide whether a message goes into your topic. You can have up to 2,000 subscriptions on a singular topic, and you can actually have up to 2,000 of these filter rules on a per subscription, through which you can make decisions of whether you want to have your messages. The subscription rules can decide based on the message properties. The message properties are part of the message. We have a model of messages that's loosely aligned with AMQP 1.0, but we have it's really an abstract model because we can go from HTTP to AMQP very easily. So you can send a message in through HTTP, you can receive it through AMQP, you can send it through AMQP and receive it through HTTP, and we're mapping this through this abstract model. So we have system properties, we have application properties, and we have the body of the message. The body is something we never touch. The application properties is something that's your thing. You can go and put arbitrary properties in here. You can also have no body at all and just put your data into the properties if you want to. And into the system properties goes everything that the broker needs to understand. The application properties can be used for filtering in these subscription rules. So you can make these SQL 92 expressions, and with that basically target your data stream towards particular partitions, or filter which messages you want to go and see. There's 3 delivery options. One is receive and delete. You can pull messages out very, very quickly, and the messages are deleted from the broker as they are being put on the wire effectively, which makes it fast because you don't need to go and acknowledge them. But if the message is lost on the wire, if the transfer is abandoned, then you lose that message. So it's a fast way, but it's a more risky way. It's what we call at most once. Peak lock is an at least once mechanism. You take the message out. The message stays in the queue over there. It's being locked, as we call it, and then you get the message. You can process the message, and then you say unlock in the .NET API. And there's other gestures in the other APIs, you say complete in the .NET API. And there's other unlock gestures in the other APIs, by which you confirm that you have the message received, and then only then does the message get deleted. That gives you reliable at least once delivery. And then there's a session model for this, which is similar to peak lock, except that all the subsequent messages that have the same session ID also get locked alongside with it, which gives you strict order guarantees that we enable by sessions. That's a special feature that we have in Service Bus. Back to the forwarding capability that I mentioned in queues. The forwarding capability allows you to go and create compositions of queues and topics. You can create, for instance, scale out topics. You can create a tree, as you can see here. You can send a message into a topic, and you can have a subscription then forward onto a further topic. So you can go and make a topic that has 100 subscriptions, and then you can add 100 topics which each have 100 subscriptions, and now you can go and send out to a further population, but you only sent one message in. That's what we call a fan out tree. You can do a fan in, where you let queues take a set of queues take the initial load if you have extreme bursts, and then you can go and trickle them down into one consolidating queue. And that consolidating queue, the pumps that are doing this can't overstress that consolidating queue. You can also have different writes, different access control rights on different queues. So you can also use it for that, and you can use it for route decoupling. So you can give a client a particular queue that they will go and send all messages to, and you can go and change the forward to property on that queue, which means you can decouple the input and the output, and you can flexibly rewire them inside of Service Bus. So that forwarding capability is a very, very powerful feature. And then lastly, also something we haven't discussed here in Subscribe yet is a partitioned entity capability. And the partitioned entity capability is something that exists in Service Bus in the cloud. And what that gives you is a queue or a topic where the log is actually split up across multiple storage backends. Effectively, you get a thing that looks like one queue, but really is a set of parallel queues. What that breaks is absolute order. So if you care about that, you don't use a partition queue. But most scenarios, you don't need absolute order across the entire stream, but you need at most per source order, which you can go and control here, because we have a way to go for you to control a so-called partition key. And with a partition key, you can keep all the related messages together. And what that gives you is, if any of our backend storage systems should be slow or should have higher latency, that will even it out. It's a reliability feature that we have on by default. Partitioned entities, so one queue doesn't have one log, but one queue is actually spread out across a number of logs, which gives you better performance and better reliability, really all up. We have more features in Service Bus queues and Service Bus topics. There's just a list here. We support batching. We have dead letter capabilities, duplicate detection. We have entities. You can create a queue and you can have that queue expire. Messages can expire. We have multiplexing through a queue, so you can send multiple independent streams. We have scheduled messages. You can put a message in, and it can show up 3 hours later in the queue. We have session state management for workflow support, and we support transactions. So you can build very many sophisticated applications with Service Bus, and we're going to go into depth on many of those features in future episodes. Most of those capabilities that I talked about so far are consistent, with the exception of partitioned entities, consistent across cloud and on premises. The reason why you want to run in the cloud typically is cost. Specifically, when you are already building cloud-based applications, you may be tempted to go and install your own message broker. Maybe Service Bus, maybe a different one. The Paas system, so us running the broker for you, has some very strong advantages. First of all, it's instantly available. You don't need to set anything up. You don't need to go and provision any VMs. You don't need to monitor those VMs. There's no deployment effort. You don't need to write any scripts. It's just there. And it speaks a standard protocol that you can talk to from effectively any language or any platform, from Node through PHP, through Java, through .NET. So you don't need to worry about storage. You don't need to worry about software licenses or maintenance. We give you financially backed SLA. And we do deal with automatic failover, and we do disaster recovery, which means if the data center were to burn down, we can go and stand up your existing workload with your data in a different data center, because we're doing continuous replication between those places. That's something that you don't need to set anything up for. And obviously, when we upgrade the system, we do this with no downtime. We flex it. We have our clusters are big enough that we can take parts of them down, and they're designed in a way that downtimes don't affect the system even under load. Service Bus standard. So the standard product in the cloud that we have is available in 15 plus global data center regions. We have relayed and brokered messaging inside of there, queues and topics as I mentioned, the MQP protocol, HTTP REST protocol, and how that's implemented is over effectively shared resources. It's a multi-tenant system. You put your queues in there and they run on our resources, which gives you the economics of a multi-tenant scale system, which means you're leveraging shared resources and the price is very low. The price is very low, but the quality is very high. You get a world-class, high-scale, highly available, highly reliable system. Our communication gateways, which speak AMQP and which speak HTTP, are scaled out. They're stateless gateways up to 128 nodes, 128 machines per service bus cluster. The messaging capabilities run in a specific subsystem backend. That's where your queues and your topics are being managed. A queue and a topic has one primary owner at a time. There's secondaries which keep the state, keep track of that state, which the data gets replicated to. And then it's backed by a log store, which also is replicated. And the nice thing is we are dealing with all the failure conditions, and we're dealing with machines going down and upgrades and replenishing machines that have gone down automatically for you. So the queue is owned by a broker, and that broker is writing to a log, or as I talked to you about it, partition queues, multiple logs. And should one of those brokers fail, then we're failing over to a secondary. If should the log fail, then of course we're also failing over to the secondary. You don't need to worry about those things. That just happens automatically for you. In a fairly large cluster, so there's we don't run out of resources and we automatically go and stand up that second machine for you. If you were running your own broker, you would probably do a setup with like a cluster of 3 or 4. If your broker technology even supports anything but a hot-cold setup, active brokers are not so common. And so if you support this, then and one of your machines dies, then you have to go and replenish and have to rejoin that machine to the cluster and all this, have to do all that work. You don't have to do that here at all because we just do that for you. With Premium, you get all those capabilities. You get all the automatic upgrade, all the automated management and all those things, all those features. But we have now taken effectively the concept of standing up your own service bus on your own resources, which gives you isolation, which gives you your own CPU, it gives you your own memory, it gives you your own storage. We've taken that concept and basically built a model where you get a cluster inside the cluster. You can reserve yourself those resources in the form of a messaging unit. The messaging unit is something that we don't call VM because it's not quite like that. It's very similar to a VM in that you get a guaranteed core. You get actually more than a single core, but let's stick with me for a second. You get a core and you get allocation of memory, like 7 gigabytes. In fact, you get more than this because you also get secondaries. So you get a primary with a messaging unit, and that messaging unit is roughly equivalent to a core plus memory. The secondaries also count because the data that comes in gets replicated to effectively what is a secondary or a set of secondaries which are candidates to become a primary for you if your primary fails. So you don't get one core, you actually get more than one core, and you get more than that 7 gigs of memory. And that's why it's a messaging unit, because it's something that is reserved space in the cluster. We never over-provision the cluster. We actually under-provision the cluster significantly to have enough reserves. And that messaging unit is now processing your messages. All of your queues and your topics are being handled by your messaging units. One namespace can have 1, 2, or 4 of these messaging units, which means you get the rough equivalent of a 4-core clustered machine with secondary reserves in your cluster. So you get effectively IaaS performance, IaaS infrastructure as a service like isolation. And with that you get predictability. because a lot of the work that's being done specifically in enterprise messaging, all the features that are enumerated, duplicate detection, session management, etc., are very CPU and memory intensive. And now you're no longer competing for those resources with everybody else in the cluster, but these are your resources that you have. And again, you get effectively the flexibility and the failover and the management. You don't need to worry about your own VMs, etc. You get that by us having a mixed model of having dedicated resources that work like a cluster inside a cluster inside of that broad multi-tenant shared managed platform. And of course, in terms of throughput, what you get also in messaging is our new Jetstream engine. The Jetstream engine is the same engine that we built for Azure Event Hubs, where it processes over 1 trillion messages per month. And that Jetstream engine has been now updated to support all the extra features for queues and for topics. The Event Hubs are a very powerful, very broadly scalable pass-through mechanism. And here we are doing a lot of processing in addition, so we need to do a lot of indexing, etc. So we've added those capabilities to that new Jetstream engine, and that's now available to premium messaging customers. So premium messaging is exactly like Azure Service Bus Standard in terms of capabilities, but it gives you these exclusive compute and storage allocations through which you get more predictability, and that's the theme for Service Bus premium messaging. And what you'll see is that as we're adding more features to Service Bus messaging, most of those new features will be showing up in premium first, and also premium is giving us more ways to do things that are compute bound now, rather than things that are just purely I/O bound. So Service Bus Standard is going to stay fairly simple in terms of compute capabilities or compute demand capabilities, and premium messaging has some more headroom to take those on. So to draw a comparison, really, Standard is reliable. I have a jumbo jet here, and a big fan of the jumbo jet. So I'm also a big fan of Azure Service Bus Standard. It's a very efficient use of shared resources. With the jumbo jet, 350 people can fly in a single jumbo jet. High performance reliability, standardized management, standardized protocols. Sometimes you need to have the dependability and the predictability and the individual needs to go have a private jet. And that really is what premium is. Premium is the private jet compared to the commercial jetliner. It gives you dedicated resources, and you get predictable and reliable performance that you can control by selecting how many messaging units you want. That also has effects on pricing. In Service Bus Standard, you are being charged on a per transaction basis. You have a base charge of $10 a month with some inclusive message volume up to 12.5 million operations per month are included. And then the overage is being charged on a per transaction basis. And with Service Bus Premium, the pricing is predictable, which means you are paying for the resources and as many transactions as you can execute on those resources. So $22, $26 per day, it's a daily charge per messaging unit. These are prices that are going to be effective at general availability, and we're going to have a reduced rate as we are as long as we're still in public preview with Service Bus Premium. So there again, the pricing is predictable. It's not tied to transaction count. It's actually just tied to how many resources you're buying, you're renting effectively, how big you make your cluster inside of our cluster. So summary, Service Bus Standard, fully managed Paas infrastructure, available worldwide, wherever you want it, 15 plus data centers around the world, fully standards-based, pay-as-you-go pricing. And then premium, you get the cluster within a cluster, all the capabilities and reliability and all the management advantages of a Paas infrastructure, but you get reserved capacity for higher predictability, higher performance through the new high-speed storage engine, and of course, predictable flat rate pricing. And with that, I would like to thank you for sticking with me, for listening to this baseline presentation about Azure Service Bus, messaging capabilities, from server through standard through our new premium SKU. And I hope I give you a nice overview here. We will continue on that path, go into details, actually do a developer overview, first in .NET and then in a bunch of different languages to show you how to unlock the power of Service Bus in your own applications. Thank you for listening and bye.